Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just go over a few of the kind of most important problems from this first semester so far. So one of the big things that you'll start to see a lot more of in linear algebra is problems kind of phrased this way, where they're talking about linear transformations. And you'll see this kind of notation a lot, like the name of the transformation, and then this is telling you it goes from here to here, right? And then this is the instructions for kind of how the transformation works. So, this x1, x2, x3, whoops, it's a bad line. x1, x2, x3 is like related to that. And then the fact that there is one term there, two terms there, and then three, right, is related to the fact that it lands in R3. And here I'm just asking you to write a standard matrix representation of T, which in this case you can basically do by looking at this part, right? So it's saying that we have like, basically I'm just going to fill in 3 rows that relate to 1, 2, 3 different parts here. And, I'm thinking about it in terms of like one x1 column, an x2 column, and an x3 column. And so this would look like there's 2x1, and then 3x2, and then no x3. And then the second row is like no x1, no x2, but 1x3. And then 4x1, negative 2x2, and then no x3. And so that really is the matrix that represents this transformation T. That's what we call that standard matrix representation. And the question next is T invertible? If so, find it. The way I would personally just do that is I would augment this thing with the identity and just see what this gives you, right? So if you RREF this, just like practically every problem in linear algebra, you would get this. And what this means is that, since basically this identity is flip-flopped, what we've really done is we've solved for what the inverse is over here. This is that Gaussian reduction method to get the inverse. So this matrix is like, we'll call it T inverse. And if you do, if I call this one T, and you just truly do T inverse, you'll get the identity. And also if you do T inverse T, you'll also get the identity. But that's it. All right, so these are just some kind of important concept questions. So just going to kind of talk about whether or not these statements are true or false, and just kind of talk about each one a little bit. So the first one says, if V is a subspace of R5 and V is not equal to R5, then any set of 5 vectors in V is linearly dependent. So if you think about it, so if V is not equal to R5, right, then the way my brain thinks about it is like, suppose V is like R4, okay, which is like, the biggest it could be, and yet still not equal to R5, because it is a subspace of R5. So it has to be like, R4, or like R3, or like R2, or like R1. Or I guess it could be the trivial subspace 0. But if you have any set of 5 vectors in R4, then certainly they're going to be dependent. So yes, 5 vectors in R4 are dependent somewhere, right? You might have like 4 of them being linearly independent. You could have like I hat, j hat, k hat, and then we'll call it w hat for the 4th one. But then as soon as you introduce a 5th vector, it's going to be dependent. All right. So that one is true. then the second one says, if A is a 4 by 7 matrix, and if the dimension of the null space of A is 3, then for any like vector in R4, like B, the linear system AX equals B has at least one solution. So the way I would think about this one, if we take the null space of A is 3, right? That means the dimension of the null space of A is 3 is basically a definition of the nullity of A equals 3. And we know that from the rank and nullity theorem, the rank theorem, that the rank and the nullity, so the rank of A plus the nullity of A have to add up to, like, for an m by n matrix adds up to this n right here. It's like the 7. This is like the size of like the output, basically. It's saying that like the stuff that gets mapped to 0 and the stuff that gets transferred through the transformation have to add up to where you land, right? So it has to add up to 7. So what? So 4 plus 3 is 7. I love writing these kind of equations in a college course. And so this matrix A, has rank 4, or 4 like non-zero rows, right? Remember, rank is like the dimension of the row or column space, and you can also just think of it as the number of non-zero rows. And so basically, if you think about it that way, you've got a matrix that has like, it's going to have basically a bunch of zero. It's going to have some non-zero rows, right? And so there have to be a solution to, if you start with a vector in R4, there's going to have to be a solution because there's some non-zero rows, and it goes back to the idea of like if you had a matrix just like I don't know, let's say it was like 1, 2, 3, 4, then actually I'm gonna make just 0, and then 0, 1, I don't know, 1, 2, and then 0, 0, 0, 0, right? Like this thing has like an infinite amount of solution basically between these 3 planes, and like this is like the row reduced one. It's basically what we have going on here. So yes, this is also true. It all just ties into the rank theorem. All right, so this last one just says any 4 linearly independent vectors in R4 are a basis for R4. And that one is a very, very solid true. It's basically by definition. If you just think about the definition of a basis, right? It is, they're just linearly independent vectors that span the space, right? And so 4 linearly independent vectors in R4, right, would span R4. And so, yeah, that one's like a pretty clear-cut true. So all these are definitely true. All right. Another really, really important idea is just finding these basis for kind of the big 3 subspaces that we've seen so far. So the row, column, and null space of a matrix. And so I just want to go through and do that for all of these. So probably the longest one is the null space one. So I'm actually going to start with that one just because. So, this is like the vectors but the matrix sends to 0. And so the way we start this thing off, so we got to start by basically setting this up, and then in a matrix, and then REFing that thing. So we're going to start with this matrix, and we're going to do our REF. And if you just pop it into a calculator, you're going to get 1, 0, 0, 1, 0, and then 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, and then a row of zeros. And then that means from here, right, we can see x1 equals -4, like x2. x2, I'm sorry, I don't know why I said x2, probably because I was thinking ahead. I also don't know why I said -4, because I was probably also thinking ahead. x2 equals also -x4, and x3 is -x4. And so basically this is one where if you just let x4 equal t, right, then we're going to have kind of a general vector of the form -1, -1, -1, 1, right? And so the null space is actually the span of this, it's like the set of all these linear combinations of this vector. But an actual basis we could take is just that one, like without the t if you want. That could be a basis for the null space. Should add that part too. All right, and that's basically I think that one is always like the most work. The other ones are not too bad. So let's do those now. All right, so so let's just do row space now. So for a basis for the row space, the way that we've done it is we just take the matrix, we do our REF. In this case, we get, we're actually just going to get this, just without we didn't augment it with 0. So we're going to get 1, 0, 0, 1, and then we're going to get 0, 1, 0, 1, then 0, 0, 1, 1, and then a row of zeros. And the way we found a basis for the row space is we basically just took the looked at the non-zero rows, and each row here is a linearly independent vector based on like the RREF and how that works. And so you can just take those three vectors as a basis. So the basis for the row space would just be the set of vectors 1, 0, 0, 1, 0, 1, 0, 1, and then 0, 0, 1, 1. And then last but not least, we're going to do the basis for the column space. And the way that we kind of talked about this before is we can actually just do the RREF of A transpose. And if you do that, you will get that. And then we're going to do the same kind of trick. So we can just take a basis here for the column space to be the set of these three vectors in the row the row reduction of the transpose of A. And so we get 1, 0, 0, a quarter. And then we get 0, 1, 0, 1 again. And then we get 0, 0, 1, and 3/4. And that's it. So yeah, and if you look kind of, a big part of linear algebra is like analyzing these linear transformations and matrices and all that. And it makes sense that the basis was a one-dimensional space, right? This is like a line in R4 that cuts through the origin, right? And the row space or something, or the column, is a three-dimensional space, right? And we know that because this is like a 4x4, that 1 plus 3 should add up to 4. they have to match up in order to get to the size of the matrix. All right. So this question, just another good kind of concept question. So we did this a long time ago, but they're still really important. Finding the distance between parallel lines is just one of these things that uses a lot of good vector calculus tricks, and there is some stuff that we're going to do next semester that uses projections and other things. So I kind of want to just do that here. So the idea with these problems is you'll have two planes, right? They're parallel. So you've got this. Oops. This plane. Okay. And what we're going to do is we're going to pick a point in each plane, and we're going to create a vector that goes between the 2 points, right? And then we know that we can get a normal vector to, either plane, really. And then the idea is we're going to project, let's see what color I want to do. So we're going to project this yellow thing over onto the normal vector there. And what that'll do is it'll scale the normal perfectly to, even if the normal was past here, it will still perfectly scale so that this is the true distance, the vertical measurement of that distance between the planes. So that's the way we're going to do it. So start off, I'm going to get the points on the plane. So 1 point on this first plane, and I always try to look at what is an easy point, okay? So definitely -3, 0, 0 is on that first plane, all right? And then over here, 3, 0, 0 is on that plane, right? 6 times 3, 18, then you just pop in zeros here. So my my vector v, my yellow vector, is just going to be -6, 0, 0. Okay, and so that's just -3 minus 3, and then the normal vector is just the coefficients of really you can take it of either plane. So let's just, these are smaller numbers, so let's do it with this one. So you can do -3 to 1 as the normal, okay? If you did this, it's just a scalar of that, right? So smaller numbers are better. And then the distance will just be the magnitude of that projection of v onto n. And so that looks like n dot v up here, and then n dot n down here, and all of this is times n. Okay, so we're going to get 18 there for the top dot product, and then we're going to get 9 plus 4 plus 1, and then it's times -3 to 1, and we're just calculating the magnitude of that. And the magnitude of that thing is 9 square root of 14 over 7. So, it seems kind of silly because this is very much a Calc 3 problem, but there's going to be a lot of, this is a very linear algebra problem because we're dealing with linear things, and there's some stuff coming up down the road where doing this kind of thing is going to be important. So I don't want you to forget about it. So very important Calc 3 problem, really, but it shows up in linear algebra because it has to do with linear things. All right. So this question is just, a proof, a very important kind of proof where we're basically asked to show that something is a subspace, and it's a very specific one. It's the null space. So prove that the null space is really a subspace of Rn. Something I don't think I've ever done, but there's basically 3 things to check. And it's really important you know the definition of a subspace. And one of them was that the zero vector is in the space. So kind of condition A, note A times the zero vector equals the zero vector. Yep. The zero vector is part of the null space of A. Sort of trivial, but really important. If you don't have zero in there, you're not going to be able to do a lot of nice linear algebra stuff. Another property is that if you have, so we're going to let U and V be in the null space of A. So basically AU equals 0 and AV equals 0. And another nice property, another like property of a subspace is the closure with addition property. And so if you take any two things in your subspace, you can add them together and they'll still be in the subspace, is the idea. So let's just do that. So if we have AU plus AV, right? This is, you could take, actually I think I want to start that off differently. I want to say, I want to show that A time operating on U plus V is in the space. That's what I want to show, sorry. So then I'm going to distribute, and I get AU plus AV. And we know by this line, right, since U and V are in the null space, then we would get that this is like 0 plus the 0 vector, which is 0, not a 6. And so this shows, really proves the closure by addition property. And the last really important thing to check is that the closure on scalars. So basically, given a given like some C in the overall field that we're in here, like Rn, that you can scale the vector by that, and it stays in the subspace. Okay, and so so we're going to let C be in Rn. Okay, and we need to show that A times C like U equals 0 for U, any given U in the null space of A. Okay, and it's honestly not too bad at all, because all you got to do is like just say something like note ACU equals CAU, which equals, jump down here, C times 0 vector, because U is in there, which equals the 0 vector. And that does it. Knowing how to prove something as a subspace is like a very important thing in linear algebra for sure. So need the 0 vector, need closure by addition, and closure by scalars. So very important problem. All right, so for this one, I have a matrix A, and there is a pattern that will rise for A to the n, and then I want to prove that that pattern holds for all n in the naturals. And so to do something like this, you just need to kind of jump in and start trying powers of A. So if you do A squared, okay, you should double check that these things work. And really, like always, I would encourage you to try these problems before I go over them. But A squared, if you do it out, so if you do A squared out, you're going to get 1, 1, 3. Then you're going to get 0, 0, 1. Then 0, 0, 1. And if you do A cubed, so if you just do A squared times another A, okay, which really would be like, we would do it on the left, right, like that. We would get 1, 1, and then this time we would get 5, and then we'll have 0, 0, 1, and then 0, 0, 1. And you might start seeing it there, but you might need to do one more out. But it's probably not too hard to see that the pattern is basically this. The pattern looks to be, at least, 1, 1, 2, n minus 1, and then 0, 0, 1, 0, 0, 1. And so we're going to try to prove that that pattern actually is true for all n, okay? And we're going to use induction, of course. And so I'm going to start off with my base case. So I'm just going to say, like, note, a to the first equals, 1 times 1 times 2 times 1 minus 1, 0, 0, 1, 0, 0, 1, right? Because this really does simplify to 1, which is equal to a, which I guess I should say which equals a. And so that's my base case. And then I'm going to assume that a to the k equals 1, 1, 2k minus 1, 0, 0, 1, 0, 0, 1, and show that a to the k plus 1 equals 1, 1, 2 times k plus 1 minus 1, 0, 0, 1, 0, 0, 1, which you could simplify to 1, 1, 2, what would be k plus 1, and then 0, 0, 1, 0, 0, 1. And, there's once you do enough of these, they really start to be, they feel kind of very similar. So what I'm going to basically do is I can work with ak plus 1, assuming this, and I should be able to start here and get to this using that, okay? So we have ak plus 1 equals a times an a to the k, which if I use my inductive hypothesis, right? Whoops, that's a 0. That's my a, and then I'm multiplying it by 1, 1, 2 to the k minus 1, and then 0, 0, 1, 0, 0, 1. And then if you do this out, okay, you're going to get 1, because you're just doing 1 times 1, and then you got zeros times these guys here. So that's just 1, and then 1 times 1, and then again zeros, so that's a 1. But now you have, in this last one, 1 times 2 to the k, 2 to the k minus 1, and then you have plus 1, right? And then likewise, the other stuff is just going to work out to 0, 0, 1, 0, 0, 1. And that thing in there is truly, 2 to the k plus 1, because you can cancel 2 of those right there, or that negative 1 and plus 1. And you would get a to the k plus 1. And like any proof, you would want to kind of add a few filler words to make this read a little bit better. But this is a very common kind of thing you see in like a lot of papers out there where people need to show that some pattern really holds for all naturals. All right, so really quickly, I just want to do kind of 2 more just quick concept questions. So write down a non-zero matrix which is non-invertible, and give an algebraic and geometric reason why your matrix is non-invertible. So a really easy way to do this is to just pick something that is not square. So if you do a equals like 1, 2, 1, 1, 1, 1, this thing is sending 3-dimensional thing to a 2-dimensional thing, okay? Because it's a 2 by 3 matrix. And, if we're losing dimension like that, then this implies that the determinant of this thing equals 0, okay? And so the, kind of algebraic reason why this thing has no inverse is the determinant equals 0, and the geometric reason is you're losing dimension. so you wouldn't be able to unpack it and get the inverse. All right, in the last few seconds, because I ran out of time, this is a matrix that would do this. There you go. We can talk about it more in class.